Exercise 8. This one is a little tough to fit on the screen, so I'll probably have to scroll down at some point, but yeah, just make sure you have a copy on the hand, or you might have to write the problem down. Whatever. So we're going to start going through this. It's actually kind of nice, kind of a neat argument. So x is an Rn. Be the jth, we'll just call it the jth coordinate vector. You know what I mean. It's just the vector looks like all zeros except you've got one at the jth spot. Say t not equal to 0 and ej, let this, and this be blah. Okay, so this works. Then we have 0 is less than or equal to the absolute value of something. So what we're going to do is we're going to write something that's going to turn into a derivative, because what we're going to want to do is we're going to want to pass a limit as t goes to 0. So why are we calling it t instead of h? T is a little easier to write, I guess, maybe. I don't know. Who knows? I'm going to stick with this. So this, which is going to become the derivative of f star g in the jth direction, which we know exists. And this is, and we're subtracting dj f star g x. And when I mean this, I'm going to be very clear when I want to take the derivative of f star g. So here I mean, I'll just write the parentheses. It's the jth derivative of f star with g, this whole thing evaluated at x. And what's this equal to? This is just equal to, well, let's write out the integral. Integral over Rn. We'll keep the t inverse inside. This is f of x. Once we write out the two integrals on this left side here and subtract them, what we're going to get is we're going to combine the f's together and we get this gy out here. And then you get minus, and then this is what we've got on the right side. We've got djf evaluated at x minus y, and this times gy dy. This all in absolute value. And what's this equal to? This is equal to rho of r over n, t to the minus n. We're going to write this using tau because that's going to look a lot like the thing that we want to make it look like this. And so that's what we're doing. Fx minus y minus fx minus y gy dy minus, and then we've combined these two integrals, and so this is minus djf x minus y, and let's see here, this gy I want to put on the outside of everything. So we're going to move this over here. Do I have this right? I do have this right. This is gy dy. But then this is going to be less than or equal to the, we bring the integral, the absolute value inside, and so I'm just going to write it Rn, this dy, just out of laziness. Actually, I'm going to write it as this time, oh, that's a little, should I write here? Just draw like a blob. So you just put all this stuff with the f's here and put that in there. We multiply this by the absolute value of gy dy, and then by Holder's inequality, this is less than or equal to t inverse tau minus tej of f of x minus, and this is going to be with respect to y. So minus fx minus dot minus djf of x minus dot, and this is not Morse code, this is me saying this is x minus, and then this dot is just the variable that's being integrated over. That's kind of standard notation for LP spaces. Then this GQ. But the Lebesgue measure is translation invariant, and so what this is equal to is we can replace these x minus dots with just the LP norm, and so this is just T inverse of T minus TJ F minus DJF, the P norm of this GQ. Now, GQ is fixed, and by the definition of the LP derivative DJF, we know that the limit as t goes to 0 of this whole thing, tau minus TEJ F minus F, so here, and this is minus DJF P, this whole thing is equal to 0. Let's see here, am I off by a t here? Because if we, basically what we want is we want it to look like this. And the one thing that's not quite right here is that if you multiply this out, there should be a t inverse there. I know what it is. It's right here. I brought this in without accounting for the t, so I'm just going to multiply this guy by t. And I'll put this t in here, and I'll put this minus this. So here we've canceled the t and brought it back out. Alright. This minus this. This is equal to 0, because in the limit, that's just what it means for this to be an LP derivative. Okay? So, by the squeeze theorem, it's a great theorem, it's a great name, it tells you exactly what's going on, because you're squeezing stuff, and you use it like from calculus all the way on. 0 is this limit of T inverse of f star g x plus tej minus, and then we've got f star g of x, then minus dj f star g x. But then, let's see here, what is this limit? This limit is equal to, if you bring the limit inside, which you can do because this is an absolute value sign, this is just, yeah, let's be a little more explicit here. We've got djff x plus g here, and this is being evaluated at x, minus djf star g, this whole thing evaluated at x. So dj f star g of x exists and equals dj f star g evaluated at x. Now this holds for all x in Rn, and hence dj f star g is equal to djf star g. Alright, and oh, well, you can see it's just peeking out a little bit there, that this is the exact thing that we were looking for. And so this completes the proof.